Hello fellow programmer. Today I want to show you how to compute the LCA, the lowest common ancestor, in constant time. This requires that you know how to answer range minimum queries in constant time. If you don't know how to answer those, then watch my last video about the sparse table, where I talked about this topic. Now let's get started. The lowest common ancestor is defined on a tree. We have the following tree. Each node in the tree has an ID, an index. Let's say this is 0, 5, 7, 2, 3, 1, 6, 8, 9, 4. And now we highlight two nodes, for instance the node 3 and the node 8. You want to find the lowest common ancestor. The ancestors of a node is just a list of nodes that include the node itself and the parent of the node and the parent of this parent and the parent of this parent and so on. For the node 3, the ancestors would be the node 3 itself, then the node 1, the node 5 and the node 0, all the parents above. And for the node 8, the ancestors would be the node 8 itself, then the node 5 and then the node 0. And now from these two node lists, we want to find a common node, so a node that appears in both lists. These are only these two nodes that are common. And then from these nodes, we want to find the lowest one. In this case, it would be the node 5. So the LCA of the nodes 3 and 8 would be 5. Why is this important? If you know how to compute the lowest common ancestor fast, then you can also compute a bunch of other stuff really fast. For instance, if you want to find the shortest path between the node 3 and the node 8, the shortest path between the node 3 and 8 visits the ancestor. And so if you have information about the lowest common ancestor, then you can also compute things like the length of the shortest path between two nodes in constant time and a lot of other things. Now let's get started. The technique behind computing the lowest common ancestors is to generate an Euler tour. An Euler tour is a tour that starts at the index 0 and visits all nodes in the tree. So first from 0 to 5, from 5 to 7, from 7 to 2, then back to 7 again, back to 5, 1, and so on. And after visiting all nodes, we end up at the root itself. And there is a really nice representation of this root. We just generate the list with all the visited nodes. So here we can use 0, 5, 7, 2, and so on. But there is one important condition that we have to satisfy before we can generate this Euler tour. We want the following condition to hold. The index of a parent node has to be smaller than the index of a child node. We will see later why this has to hold. If you look in our tree, this currently doesn't hold. So for instance here, we see the node 7 has a bigger index than the node 2. Or the node 5 has a bigger index than the node 1. And there are other examples. One simple solution is to just generate new indices. While we compute the Euler tour, we just generate new indices each time when we encounter a new node. So let's start. And we can compute this Euler tour just by doing a depth first search. So we start at the root. This is a new node. So we give it the new index 0 and we put it in the Euler tour. Then we go down to a child of 0. Here we have a new node that we haven't encountered yet. So we give it the index 1 and put it in the list. Then we go to a child of 1, give it a new index 2, put it in the list. Visit the child. This one gets the index 3 and we put it in the list. Then we go up again. This node 2 we already encountered, but again we have to put it in the list. Then also node 2 is finished, so we go up to node 1 and put 1 in the list. 1 has still a few unvisited childs, so we go down to 1, give it a new index 4, put it in the list. From 4 we go to a new node 5, put it in the list. Then we go back to 4 again, put it in the list. Go down to 6, put it in the list. Upwards to 4, to 1, to 7, to 1, to 0. We go down to 8, go down to a last node which will get the index 9, go back to 8 and go back to the root 0. So this is the complete Euler tour which holds the important condition that the index of the parent is smaller than the index of the child. And now we are pretty much set. We immediately can answer these queries very fast. Look at our example. We want to compute the lowest common ancestor of the node 3, which is now the node 5, and the lowest common ancestor of the node 8, which is now the node 7. To answer the lowest common ancestor query, we now look in the Euler tour. We look for the first encounter of the node 5 and the first encounter of the node 7. And we look at the interval between these. So this is the first encounter of 5 is here, and this goes up to the first encounter of 7. So these are these 6 numbers. What do the numbers represent in the tree? These numbers represent the part of the tour from 5 to 7, which is basically all the numbers. Now, we know that each path between 2 nodes in the tree visits the lowest common ancestor. So we know the lowest common ancestor has to be somewhere in this yellow list. And one important condition is the lowest common ancestor has to be the smallest number in this list. So we can immediately see that the smallest number here is 1. So the node 1 has to be the lowest common ancestor. Now why does this work? Here comes the important condition into play. The lowest common ancestor is an ancestor of both nodes, so it has a smaller index. And additionally, because this is part of the tour that starts at one of the nodes and ends at the second node, this part of the tour will not visit any nodes that are parents of the lowest common ancestor. So the lowest common ancestor has a smaller value than all of these nodes, and it won't visit any nodes that are above. So it is the smallest number in this range. So pretty much this is the explanation. If we want to find the lowest common ancestor, we look in the Euler tour for the range from the first encounter of the first node to the first encounter of the second node, and we find the range minimum. And we already know how to answer range minimum queries in constant time. We can use, for instance, a sparse table. Let's see a second example if you don't believe me. Let's answer the range minimum query from the node 2 and the node 9. The first encounter of 2 in the Euler tour is here, and the first encounter of 9 is here. So we look at this range in the Euler tour. This part of the Euler tour represents the following path. The minimum of this range is here, and this is the lowest common ancestor. So we can simply answer the range minimum query. I think this is enough explanation, and we can immediately go to the implementation. And because a lot of the code will be similar to the sparse table video, I just copy the code from there. And I will quickly extract the range minimum query code to a class so that the usage is nicer for us. So this should be fine. Now let's quickly add the test case. Here we'll use the same tree as in the explanation before. Let's generate an adjacency list for this tree, which will be a global variable. I need a few more vectors. First of all, I need one for the Euler tour. Then I need to store the first encounter of each node. I also need a way to map the new indices to the old indices so that I can convert them. Let's initialize the first encounter vector. And now we can write the recursive depth first function. The input parameters is the index of the node, which we'll call v, and the node of the parent. First, when we enter a node, we have to compute the new index of this node. So int new index. And we can do this basically by looking at the size of the new to old vector. Now we add the conversion to this list. We also have to add this node to the first encounter list. Which we also can do with just looking at the list of the Euler tour. And then we have to add this node to the Euler tour. And here we use the new index instead of the old index v. Okay, and now we recursively call all children. So for all adjacent nodes u, first I have to make sure that this node is really a child and not the parent of the node. So if u is equal to parent, then we just skip this case Otherwise, we call it recursively. Now with the new parent v. And one thing we have to remember, when we go back from a child to a parent, we again have to push the parent node to the Euler tour. So this is it. Now this should be enough to compute the Euler tour. We simply call it depth first search Euler tour from the root 0, and we say the node 0 has the parent -1, which is impossible. Now we have to compute the sparse table for the range minimum query. So we simply create a new range minimum query object and give it the Euler tour. And now we're ready to go. This is everything we have to do. We read two nodes u and v. We compute the first encounters of these nodes. Now we have to make sure that these two encounters are in sorted order. So if FE1 is bigger than FE2, we simply swap them. And then we can answer the question. The lowest common ancestor with the new index is the range minimum query of the first encounter 1 and the first encounter of the second node. Notice here again I'll add 1 because my implementation of the range minimum query wants that the right index is 1 after the interval. Now we can convert this to the old index. And then we can simply print the results. And hopefully everything worked. Let's test it. Okay, new to old is an array, so we have to use square brackets instead of the round brackets. Looks good. Now let's compute the lowest common ancestor of the nodes 3 and 8. And we get the correct answer 1. The new index of the lowest common ancestor is 1 and the old index was 5. So everything worked. Let's try our second example. Node 7 and node 4. And the answer is the root 0. I will upload this code to GitHub. So if you're interested, go check it out. The link is in the description. If you don't understand how the sparse table works, you can check out my last video. I talk about the sparse table in detail there. It's a really easy data structure, so go check it out. Thanks for watching.